Hello ib1 students. Thank you for your quick tests. All of you uploaded the test. I'm going to check it during this week, and of course I will write the grades to e-register. I hope it was not too difficult to you. You will find grades in e-register. As you know, we finished a whole chapter related with thermal physics. Okay, so the major test is closer and closer and closer. So you will write major test at Thursday, okay, after the break. So it will be when today is 6th, so in 7 days it's 13th, 14th, 15th, 16th, 16th of April. Okay, you will write a major test in thermal physics, so you have a lot of time. Probably it will be the same as our last quick test. I've uploaded a few minutes before our class two tests, multiple choice and open questions, or maybe open questions per 3 points without multiple choice, or maybe I will connect both into one. I'm going to give you one grade, and you will solve it during your typical class and send me after 2 or 3 hours. I will give details. I give you details later. Okay, so let's do today something like revision. So let's do two exercises from Tsokos. It's exercise number 14, okay, and page number 145, and next will be exercise number 16. Okay, so open exercise number 14, page number 145. I hope you have pen, pencil, ruler, calculator. Okay, read this exercise carefully. You can collect 6 points, so you have to spend around 10-12 minutes. So please, when you will be ready, please turn on the watch. 12 minutes working alone. After 12 minutes, I give you a solution. I hope that I will be able to solve this. Okay, so please stop the video for, let's say, 12-13 minutes, and after 13 minutes, when you will solve, turn it again and we will check. Okay? So 12 minutes later. Exercise number 14, page number 145, Tsokos. Piece of tungsten of mass 50 grams is placed over a flame for some time. The metal is then quickly transferred to well-insulated aluminum calorimeter of mass 120 grams containing 300 grams of water 22. After some time, the temperature of water reaches a maximum value of 31 degrees Celsius. State what is meant by internal energy of the piece of the tungsten. Of course, internal energy is the sum of potential and kinetic and average kinetic energies of all molecules in this piece of tungsten. B. Calculate the temperature of the flame. You may use these specific heat capacities. Water has 4.2 times 10 to the power of 3, tungsten has 1.3 times 10 to the power of 2, aluminum has 9.0 times 10 to the power of 2. Again, law of conservation of energy. Energy which is lost by hot is taken by cold, and assumption is that no energy is lost due to the surroundings. So this hot here. The hot here is a piece of tungsten of mass 50 grams, which is placed over a flame for some time. Okay, so hot is tungsten, and then it's quickly transferred to well-insulated aluminum calorimeter of mass 120 containing 300 grams of water. So both water and aluminium, both of these objects take energy from the tungsten. So all objects here, piece of tungsten and aluminum container and water, are in one phase, which means that these objects don't change a state of matter, so we can use specific heat capacities. Mass of tungsten, specific heat capacity of tungsten times change of temperature of tungsten is equal mass of water, specific heat capacity of water, change of temperature of water, plus mass of aluminum container, specific heat capacity of aluminum container, changed temperature of aluminum container. And mass of tungsten is given. Of course, you have to write this in kilograms, so 0.05 kilograms specific heat capacity of tungsten is given 1.3 times 10 to the power of 2, so it's 130 times. Change the temperature of the tungsten. We don't know initial temperature of the tungsten, which is the same as the flame, but we know that after some time the temperature of the water reaches 31 degrees Celsius. Of course, tungsten and water and container are in thermal equilibrium, so after some time the temperature of the tungsten will be 31 degrees Celsius. Now water. We have 300 grams of water, so 0.3 times specific heat capacity of water, which is 4200, and change of temperature of water. We know that water has at the beginning 22, at the end 31, so the difference is the change of the temperature, and the same with aluminium. Calorimeter has a mass 0.12 kilograms, specific heat capacity of aluminium is given as 900, and aluminium container changes temperature from 22 to 31 because it is in thermal contact with water. So in this case we have only one equation with one unknown. I can use my powerful calculator because now I have calculator. 0.05 times 130 is equal to 6.5x. This times 31 is minus 201.5 is equal to, we have 0.3 times 4200 times this difference is 9, so it is 11,340 plus 0.12 times 900 times 9, which gives 972. Okay, so left 6.5x is equal to 11,340 plus 972 plus 201.5 is 12,513.5 divided by 6.5, which gives x equals divided by 6.5. 1925, so around 1900 degrees Celsius. Oh, it's hot. Of course, it's possibility that I've made mistakes somewhere. Let me check it again, because it's quite high temperature. 1900 degrees Celsius is very, very hot flame. So we have tungsten of mass 0.05, 130. We don't know initial, final is 31. 0.3 is the mass of the water, 224200, and 0.12 is the mass of the container, and 932 minus 22. Okay, it looks good. Let me check 1 times 31. Okay, looks good. So due to this exercise, the temperature of the tungsten at the moment when it is placed to the water is 1900 degrees Celsius. So temperature of the flame in which tungsten was kept is 1900 degrees Celsius. And C, state and explain whether the actual flame temperature is higher, lower, or lower. Okay, let's look. The tungsten is transferred from the flame to the water. At the time when it's transferred, the part of energy is lost due to the surroundings. Okay, so finally, when it's placed at the water with and it has temperature during transfer, then actual temperature of the flame is higher, okay, than 1900 degrees Celsius calculated at B. So here is higher because this. I hope it was not challenging to you. Okay, so if you didn't do this, please copy this, read this 1, 2, 3 times, copy this to your notebook. You must know because this is base exercise. When you will be ready, then next exercise. Okay, so one more I'm going to do with you is exercise number 16. Okay, so at SOCOS exercise number 16 you can collect 10 points, so 16-17 minutes. Please read this, you have to spend, let's say, 20 minutes with this exercise. 20 minutes is enough time, so after 20 minutes please turn video again and we'll try to solve it. Okay, so 20 minutes later. Exercise number 16. Volume of air in the car tire is about 1.5 times 10 to the power of minus 2 meters cubed at temperature 0 degrees Celsius and pressure 250 kilopascals. Calculate the number of molecules in the tire. So it's not challenging. You can use PV equals nRT, and due to this you can find at the beginning number of moles. So this is pressure times volume divided by gas constant times temperature. Substitute data. Remember that you have to convert temperature into kelvins. So pressure is 250,000, so times 10 to the power of 3. Volume is 1.5 times 10 to the power of minus 2. Divided by gas constant is 8.31. And temperature is 273 kelvins. Calculator, and then you will find number of moles. So 250,000 times 1.5 times 10 to the power of minus 2, and all of this divided by 8.31. Remember in denominator, so bracket 273, close the bracket, and I have 1.65 of moles. And remember, 1 mole contains Avogadro number of molecules, so you have to multiply number of moles 1.65 times Avogadro number, which is 6.02 times 10 to the power of 23. So 6.02 times 10 to the power of 23 is, I have 9.95 because I've used exact number, so 9.95 times 10 to the power of 23 of molecules. Okay, 9.95 times 10 to the power of 20, and this is 3 at the end. Oh, so number of molecules is 9.95 times 10 to the power of 23. Okay, B. Explain why after the car is driving for a while the pressure of the air in the tire will increase. Oh, and 3 points. Nice question. So let's look what happens when a car is driving. Okay, this is very important. So due to the friction, what happens with temperature of the tire? Temperature of the tire increases. Yes. If temperature of the tire increases, then what happens with temperature of the air in the tire? Temperature of the air in the tire also increases. Okay? Tire is quite hard, so it's difficult to change its volume. So let's look on the equation, PV equals nRT. If this is constant, if number of molecules or number of moles of gas doesn't change, and we assume that volume is constant, so when temperature increases, then pressure also increases. Okay, so this is the answer. Pressure increases because temperature increases. Of course, assuming that volume is constant, and you must refer to Clapeyron's equation. Okay, so this is the answer. Okay, C. Calculate the new pressure of the tire when the temperature increases to 35 degrees Celsius and the volume expands to 1.6 times 10 to the power of minus 2 meters cubed. Okay, so we have again equation PV equals nRT. What is a consequence? There is nothing about change of number of moles, so we can write that PV over T is constant. What does it mean? That P1 V1 over T1 must be the same as P2 V2 over T2. P2 V2 T2. Okay, so use odd P1. P1 is 1.5 times 10 to the power of minus 2 times V1. This is V1, so I'm going to write in correct order. So P1 is 250,000 times V1, 1.5 times 10 to the power of minus 2, divided by T1, 273 kelvins, is equal to P2. We know that P2 is calculate new pressure, so we don't know this P2, times V2 is 1.6 times 10 to the power of minus 2, divided by T2. So this is 35 degrees Celsius, so 35 plus 273 is 35 degrees Celsius expressed in kelvins. So here we have, you have to solve it, so it is 1.6 times 10 to the power of minus 2 times 273, so this is 4.368 times P2 is equal to, we have this sum of 273 and 35, which is of course 308 times 250,000 times 1.5 times 10 to the power of minus 2 gives 1155 and 3 zeros. Okay, so 1,155,000 divided by 4.368. I have a result of 264,423, which is around 264 kilopascals, because kilo means 1000, and previously the pressure was expressed in kilopascals. Okay, and the yes, so A, B, C. Okay, I see that there are no points here for this. Probably 2 or 3 points. So practically I had to spend more time than this 20 minutes. Yeah. Okay, D. The car is parked for the night, and the volume, pressure, and temperature of the air in the tire return to their initial values. So now we are talking about these parameters of the tire. Okay, a small leak in the tire reduces the pressure from 250 kilopascals to 230 kilopascals in the course of 8 hours. Estimates stating any assumptions you make. The average rate of loss of molecules in molecules per second, and the total mass of the air lost. Okay, so let's look. Here we have some parameters. We know that the pressure is initial pressure, P1, is 250,000 pascals. We know that temperature T1 is equal to 273 kelvins, and volume V1 is equal to 1.5 times 10 to the power of minus 2 meters cubed. And we want to know what is the loss of molecules if pressure drops to 230,000 of pascals. Okay, in 8 hours. And of course we have to write some assumptions and assumptions we've made. So assumption, which is very important, if you want to know what is the change of number of molecules, you have to know what happens with temperature and what happens with volume. So let's assume there is nothing about changes in temperature and changes in volume. So let's assume that temperature, both and temperature and volume are the same at the morning, because in other case it's not solvable. Okay, so now we have something like this. We know that PV is equal to nRT, so PV is equal to nRT, and now we know that both change and pressure and number of moles. We must assume that R, T, and V are constants. What does it mean? It means that pressure is directly proportional to number of moles. Is it clear? So if we know number of moles at the beginning, okay, it was, we've calculated here 1.65. So we can calculate number of moles after 8 hours by simple proportion, yes? So pressure 250,000 of pascals corresponds with 1.65 moles, and new pressure 230 pascals corresponds with number of moles which is unknown. So by using simple proportion you can calculate the number of moles at the morning. So it is 1.65 multiplied by 230,000 and this divided by 250,000, which gives 1.52, around 1.52 of moles. Okay, so let's look. What is the change? At the beginning we had 1.65 moles. At the end we have 1.52 moles. So in 8 hours the difference between 1.65 and 1.52 is amount of moles which was lost. So delta N change of number of moles in 8 hours is 0.13 moles. Okay, 0.13 moles, we can calculate number of molecules, because number of molecules is number of moles multiplied by Avogadro constant. So if you will multiply 0.13 times 6.02 times 10 to the power of 23, you will obtain, I'm going to write this here, so times 6.02, it will be 0.7826 times 10 to the power of 23, or around 7.8 times 10 to the power of 22 molecules in 8 hours. Okay, and we want to know what is the rate of loss of molecules. So we have to divide this. I'm going to scroll it a little. So the rate will be this 7.8 times 10 to the power of 22 divided by number of seconds in 8 hours. So 8 times 3600. Okay, so this is 7.8 times 7.8 times 10 to the power of 22 divided by 8 times 3600, which gives, I have result 2.7 times 10 to the power of 18 molecules, not moles, molecules per second. Okay, and this is the answer for D1. But still we have one more, D2, the total mass of air which is lost, and we have the molar mass of air as 29 grams per mole. I don't know why 3 points, because let's look in previous. We've calculated the number, here we've calculated the number of molecules lost. Or, other words, not number of molecules, number of moles, it's better. Okay, so now we know the molar mass of air. Molar mass means mass of 1 mole, so we know that the mass of 1 mole is 29 grams. And we know the amount of moles which was lost. So we know that 0.13 moles was lost, and we don't know this. So again, by using simple proportion, you can find x. So x is 0.13 times 29, and we have 3.77 grams. Okay, so this is the mass of 0.13 moles of air, and 0.13 moles of air was lost during 8 hours. So this is the mass which was lost. Oof, so not challenging, typical thermal physics questions, typical thermal physics problems. So I hope that you solved this. It was not challenging. I'm going to attach one more file to you, one more file with exercises. So please do this as a revision. Still you have to do SOCOS multiple choice questions from 1 to 10, pages 142, 43, something like that. So again, before the test, please solve exercises. I'm going to attach in PDF file. It will be 1 page of exercises plus multiple choice from SOCOS. Okay? So this is your, let's say, homework. Do this before the test. Be prepared on the test, and see you probably during the test. If you have any suggestions, questions, write me in the form of post in Google Classroom below this topic. Remember, stay at home. Good luck and see you. Bye.